some FactSage application. Then we saw with the latest presentation that it is important to use atomistic simulation to generate data and better understand fundamental phenomena that are occurring in these system. And now to complete the entire I would say a picture of studying the system, I have I would call him my friend because we know each other for a long time now, Kentaro Oishi, who joined us this year. So he's working partially with us, but it's a great addition. So I'm really pleased to have him in my team. And Kentaro is doing a lot of experimental work, and he's bringing another dimension to our project. So he's going to present something about the experimental work that we're doing at Polytechnic, mostly on DSC measurement. So Kentaro, the floor is yours. Kentaro want me to keep my camera activated, so you can go, and I may interact with you a little bit while you're presenting, so you can go on.
Yeah, good. Thank you, Jean-Philippe. So can you hear me? The volume is fine.
Yeah, it's pretty good.
It's good. Okay, just I'm not very. And okay, how is the screen? Everything is correct?
Yeah, so you can present in full mode, and that's perfect.
Oh, yeah. No, it doesn't work. Works?
Yes, it works. Yeah.
Okay, good. Okay, so thank you, Jean-Philippe. I'm Kentaro Oishi, a research associate of Professor Jean-Philippe's research group, and I'm working as an experimentalist in a group of Jean-Philippe. So in this presentation, I would like to present some experimental work we have carried out so far. And at the beginning, I officially work with Jean-Philippe for only 4 weeks. I think it's only 4 weeks now, but have been unofficially working over 3 years or 4 years. And I had a lot of discussion with Jean-Philippe every time about our research scopes and topics. And I'm 100% experimentalist. I have been doing the experimental research is over 20 years, and just I have trust the things that which are happening in real world, and they have been curious for a long time that if the FactSage calculation is really correct or not. That was my curiosities, and because if we can have both tools for simulations and experimental validations, we can definitively go to the next levels of the material designs and development, I'm sure. So which is really exciting to me. So finally, I decided to join the group of Jean-Philippe. And the one things I want to mention is that Jean-Philippe always share his curiosity with me and with the students. This is it's not easy for professors, I know. And a science based on the pure scientific curiosities, not political things. The scientific curiosity is really dominant for my research. So I'm very, very happy to work with Jean-Philippe and his group. Okay, so now, oh, no, it's the next one. For today, just I'm doing some experimental analysis for thermochemical properties and specific heat capacities. CP is really fundamental data table for FactSage calculations. And also the characteristic temperatures, melting point, decomposition temperatures, Curie temperatures, whatever is really important for the FactSage database. And also the enthalpy of fusions, which is really important for the validation of the database. So what we really want to do with these experimental things is the first, the validation of FactSage database, the second, development of FactSage database, and the third, complement atomistic simulation, atomistic simulation. These three are the points that we want to do. We want to validate by experimental results. Now, so what we many different scientific techniques exist for the characterization of thermochemical properties. Just I introduced some of them, like drop calorimetries, This is very good high precision CP measurement. We don't have it, but I put it here because I personally want it. I'm requesting John Philip to purchase one, but we don't have it so far. And the other techniques is like DTA, differential thermal analysis, which is called 1D sensors, designed specially designed for characteristic temperature determination, like a melting point temperature measurement. And for DSC, the differential scanning calorimetries, this is to measure the heat flow of the samples. So we have two different type of sensors. One is the 2D sensor, which is classical DSC sensors, diffusion bonded sensors, and heat flow measurement. So when we measure the heat of fusion, we normally use this type of sensors. And this is the next one is the 3D sensors, calibrate type sensors, which consist of 18 thermocouples and which can permit to carry out the fast CP measurement. So I will explain this one more later. And this is just one schematic of the Labosys Evo system that we are currently working. And the very unique feature of this Tetalum Labosys Evo is the interchangeable sensors. By changing the sensors, which is in euros, by changing the sensors, we can analyze DTA, DSC, calibrate type sensors for CP measurement. And simultaneously, we can measure the weight changes during the temperature scan. It's very unique. And the second unique feature is that we can measure the thermochemical properties up to 1600 degrees Celsius, really high temperatures. And historically, Ceteram has been developing the system for high temperature thermal analysis. So this equipment is really appropriate for our research work. And just I will show you some of our research work. This is one of our research work published this year in 2021 about the DSC measurement of different types of aluminum alloys for the comparison and justification of the FactSage calculations. So two different shapes of each aluminum crucibles, two different shape of aluminum alloys were prepared, chipped samples and the punched samples. Also, two different types of crucible, closed crucibles, open crucibles are used for the measurement. And this study shows that the agreement between the FactSage calculations and experimental melting enthalpy was good. And the simulated theoretical curves also agree with those those values experimentally obtained. And this work is a collaboration with the NRC Canamet in Ottawa. And I'm always very happy to discuss with Dr. Shanti, Dr. Richard, and because I found they are really, I'm very happy to discuss with them about the science, and they are really curious about the science. So this is, I found that the collaboration is very good for our continuous researches there. And one of the advantage for us for this type of the collaboration is that we can always validate our measurement is correct and accurate by comparing the measurement at the Canamet. So we are hoping to find more collaborators to validate our accuracy of the result. Now, now I would like to explain more about the heat capacity measurement. And some researchers are measuring heat capacity by using a classical DSC method. And it really depends on the quantity of the samples and heat capacity of the materials. But generally, the heat capacity, the heat flow from heat capacity changes is much smaller than the enthalpy changes, enthalpy of fusions. So the classical DSC sensor is good enough for enthalpy fusion measurement, but the sensitivity is not very good enough high for heat capacity measurement. So for this reason, the Cetaram developed a Calibrate type 3D sensors, which is specially designed for CP measurement. And comparing the existing heat capacity measurement technique, the drop calorimetry is the best, followed by Calibrate type sensors and classical DSC sensors. However, the drop calorimetry takes a couple of days for each measurement. So if we make the measurement of the samples, reference, and the bulk samples, it takes 2 weeks for the measurement for each samples. And in contrast, classical DSC measurement is very fast. It takes only a few hours, but the measurement errors, the most errors comes from the thermal gradient, but error is really difficult to control. So finally, we decided to choose the calibrate type sensors, the 3D sensors for the heat capacity measurement. In case of aluminum alloy, it takes about 5 hours for each samples. So if we measure the blank samples, reference sapphire samples, and the target samples, it takes about 15 hours for the measurement. In case of this one, in case of the calibrate sensors, the measurement time is about, as I said, the 15 hours, and the measurement CP measurement accuracy is about 2 to 4% of errors. So it's not perfect, but so far we decided to start from this point to validate the FactSage sensors, FactSage database. Okay. So this is signals, raw signals from the Labosys Evo for the heat capacity measurement of pure aluminum, 5N grade, 99.999% of purities. So to obtain the heat capacities, we need to run minimum 3 measurements. The one is a blank measurement with empty crucibles. One is a synthetic sapphire standard which is a NIST standard. And at the end, samples that we want to test. For the calibration, we follow the ASTM standard. So by comparing the experimental heat flow and the synthetic sapphire data tables on NIST standard, we can obtain the value of sensitivities for each point of measurement. Okay. So this is the result of heat capacity measurements. Black line shows the FactSage database, and the red line in experimental heat capacities by using calibrate type sensors with Cetaram Lab Evo. And the blue circle is the result of atomistic simulation calculated by Mr. Javier Jeff. He just presented at 10 a.m. this morning. So as you can see, the agreement between a FactSage database experimental data and the calculated values by Javier is very good. It's very good. The agreement is very good, higher than 200 degrees Celsius. However, the maximum errors at lower temperatures below 150 degrees Celsius is about 9%, which need to be improved. And because this furnace, this system is really designed for high temperature measurement, the heating by radiations below 150 degrees Celsius is not really stable. This is the problem. So we are currently working to solve this problem. So once we confirm that the correctness of the heat capacity measurement is good, we are going to examine the FactSage database and the result of atomistic simulation, and we will apply this model for different types of alloys, aluminum alloys, or different type of alloys in the futures. This is what I have to do for the futures. So I'm sure I can show more result for the next workshop, maybe next year. Okay, so I don't know. I still have time. Okay, so
Yes.
okay, so this is the future scope. As I have mentioned at the beginning, what we have to do from the experimental point is the validation of FactSage database, development of FactSage database, and complement atomistic simulations. So to achieve these three goals, these are the list of the experimental setup that I'm requesting to Jean-Philippe to obtain or purchasing or I don't know whatever. But this is the thing that I want. And the most important section is the thermochemical analysis sections on the right-hand side, which is highlighted in yellow. So the first glass ampoule sealers, which is because we always have to consider the vapor pressures from the samples. And if once we analyze the samples which has higher vapor pressures, which can contaminate the sensors and contaminate the systems, which will decrease the accuracy of the measurement in the futures. So this is the point that we have to get as soon as possible, Jean-Philippe. So this is the first thing that we want. And the second one is just I continue with the different slide. The Gettering furnace. This is the furnace which can provide the high pure carrier gas for thermal analysis. Okay. And currently we are using the ultra high pure argon from air liquid, which is the 5N purities, 99.999% of purities. Even this purity is not sometimes is not good enough for some element which is very sensitive to oxygen, such as nickel alloys. So first, to improve our accuracy of the measurement, this Gettering furnace is really essential for our researches. And the second is the vacuum furnace for synthesis of the alloys. And we have been experiencing a lot of problem to produce aluminum alloys by oxidations. We use some furnace, but the oxidation of aluminums prevent the formation of good aluminum alloys. So the vacuum furnace is really critical for the accurate measurement of some chemical properties. And the third, the infrared gas chromatography mass spectroscopies. And by using this one, I mean, the hyphenated with thermal analysis, we can we can analyze the evaluated gas during the thermal analysis by acetylam lavosys by using this system. So we can analyze which element has been generated from the samples during the heat, and we can analyze we can do the quantification of the elements. We can do the identification of the elements, even if it's molecular or the elements, and also that we can analyze the partial pressure of the elements in the gas phase. So it will be very useful to determine the activity of the species in a gas phase. And what I'm requesting is not the one vacuum furnace or one GCMS system. This is the system I really want, and specifically I want. And because I already get the quotation for all of them, and I sent Jean-Philippe to purchase. So we exactly need this equipment for the futures. And the next one, for the chemical composition analysis, now we have two options. One is ICP-MS, one is field emission gun SEM EDS. The right one, this system is already available in Polytechnic. So I'm not requesting John Philip to purchase the same things. But on the left one, ICP-MS, we need one ICP-MS, and because I have been working over 10 years on ICP-MS analysis, and unfortunately no ICP-MS which is really designed for metals and the alloys are not available for now. So this ICP-MS will improve our researches for sure. So the last one is the crystallography analysis, like a high resolution XRD analysis, because we run a lot of high resolution XRD tests. So if we can have one in our group, I'm sure it will accelerate our researches. And I don't know, Jean-Philippe, do you still have time?
Yes,
No.
you can present that, Kentaro.
Okay. The last one is what I really want to do is a high temperature observation system. The advanced we call high temperature observation systems. I want to show our video, how I can show the videos. Okay. This is the blade of cutters, and we can observe the surface changes during the heating of the samples. And the sample can goes up to 1600 degrees Celsius, and we can observe the growth of the grains, and we can do the quenchings with the liquid nitrogens in a few seconds. So by using this one, I believe that we can validate our kinetical part of the simulations, or we can do many things obtained by the atomistic simulations and the FactSage database. It's really a unique microscope that I want to get for our future research. Okay, so if you have any question, collaboration, and support, please kindly let us know, because we really want to collaborate with anyone, and we are really open to everyone. So if you are interested, or if you have any questions, or if you want to do something with us, please kindly let us know. Thank you very much. That's all.
Thank you so much, Kentaro. And something I can add to your presentation. So basically, you saw what we have at the moment and what is our wish list. And I see a lot of industrial here in the audience. So maybe what we've presented as our wish list is a list that doesn't exist at Polytechnique Montreal. So Kentaro is, let's say, connected with all the department, chemical department, physical department, geological department, and these equipment are not available for us. So not maybe everything here, but talking about furnaces for us would be critical to have access to induction furnace with controlled atmosphere, so we can generate new experimental sample, new synthetic sample, and analyze them with the DSC. And you saw the clear connection between what Javier has presented. So he is building a model to predict the heat capacity of different intermetallics. And what we want to do with Kentaro is to validate these calculations and improve the quality of the model that we are developing. So at the end of the day, hoping that we can get this money. And through the time, when I first started to be a professor at Polytechnique, it was maybe not clear what I needed as equipment to be able to validate my research. But over the years and over the discussion I had with Kentaro, and knowing all the available equipment that we have at Polytechnique, we ended up with a list of equipment that would be really useful for us. And as a doctor, we would like to have the basic equipment to be able to perform our surgery on the material themselves. So thank you so much, Kentaro. We'll move on to the next talk. So